Good morning, everyone. Welcome back to our ACWA webinar series. Appreciate you joining us and signing up for this. As a reminder, the webinar will be recorded as a video and is available after via our website at acwa.org/webinars. Just probably by the end of the day, I'll have it up. So if you don't catch it all or have to leave early, it'll be there. Also a reminder that EnviroTech is coming up in early June, so esa.org/envirotech. Check it out. It's virtual, unfortunately, this year. So call for abstracts is still open. Our goal is to have REMTech in person again, hopefully this year. All things going well with the vaccines. We'll know by June and we'll make a decision. So we'll go from there. But for today's webinar, we have Dr. Leland Jackson from the University of Calgary. With the Advancing Canadian Water Assets group there. So he'll explain a little bit about the group and give us a talk on a bunch of water issues and plastics issues and microplastics. And then I'll come back for the Q&A part. So I'll turn it over to Dr. Jackson.
Thanks, Joe, and thanks everybody for taking time out of your day to join the webinar today. As Joe said, what I'm going to do is talk about ACWA and its infrastructure, and then some of the forward-thinking things that our research programs are involved in. I will touch a little bit on some past things, but I'll scan over those pretty quickly. And because the slides will be available, if you have questions about those, you can reconnect with me at a later time. So let's dig right into it. What is ACWA? Well, ACWA really is infrastructure. There are three components on the University of Calgary campus, a microbiology lab, an aquatic lab where we do dose response exposures, and a stable isotope lab where we can measure various compounds as they move through food webs and trace their sources. And so this is an image that shows the facility down at the Pine Creek Wastewater Treatment Center. This is the City of Calgary's latest wastewater treatment plant, and our components are this modest building right here where we have an experimental wastewater treatment plant, an analytical laboratory in the operations and maintenance building, and then the crown jewel, according to me, 12 constructed replicate research streams. And I'll show you some closer images of these in a few moments. And you can see we are located on the banks of the Bow River, just downstream from the final UV building that the university or the city has. We have a water intake structure, and I'll show you some pictures of that. So what I'm going to do is talk a bit about some of the design features that were built into the facility to allow certain kinds of science to be conducted, and then think about microplastics, water reuse, and antimicrobial resistance as emerging areas that we hope to contribute to finding solutions locally, but of course all of these have global applications. And so to understand the plumbing, I have this schematic. So here's the Bow River again, flowing left to right. We have a water intake building. Water comes out of the river and fish and plants go back into the river. Water drops into a wet well through a coarse screen, and then that is pumped from the wet well up to a head pond that holds 5.6 million liters. That's about 12 hours of water should something happen with the pump or the supply to the research streams. And this distance is on the order of about 1.3, 1.4 kilometers from side bank intake up to the head pond. We take water off of the secondary clarifiers that the city has, and that water goes into our experimental wastewater treatment plant, which is schematized here below, and first goes through an ultrafiltration membrane module. That's 0.02 microns is the average pore size, and then from there into three different treatment modules. One is a nanofiltration or reverse osmosis, so 0.001 microns or 10 nanometers. It's the pore size there. Your hair is around 40 microns. Or an ozone module or a hydrogen peroxide module. So membrane systems and advanced oxidation systems. And the goal here is to contrast their efficacy in removing contaminants and other things, as it turns out, by looking at the same influent and then comparing what goes into here and what leaves, and these modules as well. And then we can take effluent from two of the three modules and send either process A or process B up to the research stream. So that's diagrammed here from the experimental wastewater treatment plant. We add that effluent with water from the head pond to create a ratio of mixing that is equivalent to the annual average discharge of the city of Calgary into the Bow River today. So there are 2 distribution galleries. Water goes through 10 streams, and depending on whether it's permitted for discharge or not, it goes back to the headworks if the answer is not. If the answer is yes, then the water can go to the Bow River. So this would be Bow River water by itself, or Bow River water dosed with final effluent from the city of Calgary's plant today. And then each stream is organized with 10 pool riffle combinations, so we can look at footprint length, we can look at the uptake and transformation and fate of chemicals and other things as they leave the distribution gallery, this starred pool right here, and go down to the collection gallery at the end. So this is about 320 meters in length each. So when you put it all together, it looks something like this. And so it's all integrated together. And that's one of the key things that is different about this facility. We've integrated the infrastructure within a functioning wastewater treatment plant, and we've also integrated the laboratory with the treatment plant and the research streams. And so everything is on site, designed to look at a variety of emerging problems. So one of the things I just wanted to touch on was the scale of the science we do. So we can do experiments in the laboratory in small bottles. We have high signal, lots of precision, lots of replication. The challenge is when we take the information we learn there and we go out to whole ecosystems or the field, often we can't directly translate the learnings to the field. So we have 40 or 50 years of data from environmental science and technology meetings on the response of chemical A on some response organism, but it really doesn't tell us what happens in the field. And the reason is lots of things happen in the field besides exposure to a single compound. So we've followed the design model of the experimental lakes area in northwestern Ontario. We're not exactly whole ecosystems, which ELA truly is, but we're in this divided ecosystem to sort of whole ecosystem range where there is noise, there is variability, but certainly the results are very general in terms of their application to the natural world. So I'm going to go back to that intake structure and describe it and a couple of the design elements to facilitate some of the science that we're conducting. So we started by building a cofferdam and then pouring a concrete slab in place. And then we brought in precast concrete blocks. They look a little bit like Lego blocks to complete the rest of the structure. So this large cast structure right here is hollow, and there's a louver that goes on the front edge of this, and then a 900 millimeter pipe that exits here and goes to the pump station that I showed you a couple slides ago. So here's the louver. It's going in this window inside the box that you just saw. You can see these rather burly construction workers. So we're looking at about 2 meters high by about 3.5 to 4 meters wide. And the first design element is that this louver is made of stainless steel and has hollow veins through it. And so we take water from the plant in the middle of winter when our dishwashers and hot water tanks heat up water coming into our house, go down our showers, go to our clothes washers and our dishwashers, and return underground to the wastewater treatment plant. And even when the river water is 0.2 degrees Celsius, the water in the plant will be 10 or 12 degrees. And so we use the heat from that through a counter exchange mechanism to heat water that's going to then go into these louvers and prevent frazzle ice formation and do the first step in heating water up as it leaves the river. We want to run the streams 12 months of the year, and we need to heat the water in order to do that. So this heat input and another one I'm going to show you momentarily will raise the temperature to about 4 degrees Celsius, which doesn't sound like lots, but in 5.5 million liters and in the streams, that's enough heat to keep them flowing all year. This was the completed structure. Here are the sort of Lego style blocks just in the last stages of completion. And just note that there is a stainless steel railing on the top of each block that prevents kids and small animals from falling in the river and getting sucked into the intake structure. We did suffer consequences in 2013 with flooding. This is after the waters started to recede from the maximum height, and you can see we're left with a mangled block here and one block that seems to have survived. Everything else has been ripped from the structure and deposited in the river. And we did find all of the blocks except for one. There's one that it's either buried in sediment somewhere or it's in Bassano Reservoir. We're not quite sure where it ended up. This is the second style of heat exchanger. It's a series of plates, and again, it's passing warm water by cold water with those plates, and that is the second stage of heating water up. So when we built the streams, we wanted to create naturalized systems, but we wanted to have the capacity to add emerging contaminants without contaminating the aquifer. So we laid a clay pad that's about 200 meters by 400 meters, 2 to about 4 meters deep, and then carved channels out of the clay, and then laid pit run gravel into the channels to create the pool riffle combinations that I talked about in the schematic, and we'll show you momentarily. So here's an individual who is, this is Carrie McDonald standing in the finalized channel, jumping for joy at the end of construction. And so you can see a little bit of scale of the depth of the beginning of the channel construction. This is post filling in with the pit run gravel. We laid these rocks in by hand. So 12 streams, 10 riffles is 120 riffles to do this in. Whoops. We were wanting to create the sort of water features that create aeration and microhabitats that you would find in Jumping Pound Creek, which is what we used as our model system. So this is minus 27C, and you can see there is some ice on some of the pools, but water is still flowing. So we accomplished the objective of being able to have water flow year round. And the reason we wanted that was we didn't want to have to reseed benthic invertebrates and fish that overwinter in the pools by having a complete freeze or having to shut the water down in November or December and then start it back up at this time of the year. And so here's a summer picture. Post-colonization, we let colonization happen naturally. You can see poplar, white and yellow sweet clover, there's some sedges, cattails, of course, sandbar willow, and lots of periphyte growing on the rocks down here. And so as I mentioned, these 12 streams are about 320 meters long each. They're naturalized, they're replicated. And so we've taken the foundation of modern biology, which is the controlled experiment, and we've incorporated that into the experimental design. And we've taken the two largest sources of variation in natural rivers, which is flow variation and channel morphology, and we've eliminated them. And by doing that, we've increased the signal to noise ratio effectively by grossly reducing the noise. And so it means that we can dose contaminants that are environmentally relevant concentrations and still measure effects. So we don't need to, set off a grenade or a nuclear bomb to see effects in the stream. So this is key in terms of informing policy and regulations development and changes. So one of the other things we did was we wanted to include the capacity to dose individual chemicals if a chemical of concern was to arrive on everybody's sort of consciousness. And so we can do that right here. You can see a ball valve. We can set up a table with a carboy and a peristaltic pump, and we can actually dose the water coming out of the head pond, which is coming through here. Raw stands for raw water. And these other 3 pipes you see here are where we dose either final effluent from the city's plant or effluent from 2 of our research modules. So all the magic mixing happens here, and the 2 header galleries are identical, and we have complete capacity over what we dose and the amounts of dosing, so the ratios that we use. And as I said, we're at about 3.5% today, which is the average annual discharge of the city of Calgary into the Bow River today. So the analytical lab is very well endowed with the ability to see things down to nanograms per liter concentrations in many cases. This is a little bit of alphabet soup, but we have the capacity to look at things that are in the liquid phase if we can't force them into the gas phase. So liquid chromatography with a couple types of mass specs, triple quad and time of flight, which we use for non-targeted screening. So a typical scan of our water going into our wastewater treatment plant will have about 8,500 peaks or 8,500 unique masses. It doesn't mean it's 8,500 unique compounds, but it's pretty close to that. It's a complex mixture. For things that are volatile or semi-volatile that we can force into the gas phase, we have gas chromatography with a variety of different detectors. And for looking at trace metals, ICP-MS. We also have a standard suite of laboratory equipment and a full microscopy suite to look at everything from benthic invertebrates to intersex gonads in fish to tagging compounds with fluorescent markers. We can look at those as well with fluorescence microscopy. So pretty nice analytical lab. And then this is the ultrafiltration module. I'm going to talk about it in a few minutes with regard to the microplastics. This is the 0.02 micron membrane system. There are 3, think of them as bookshelves, 1, 2, 3, and there are 6 books on each bookshelf. Each of those books is a cassette that contains strands of membranes that look like spaghetti fibers. And so this gives you a sense of the scale. This is about 2.5 meters tall. So the research foci traditionally have been engineered technologies, so looking at the advanced oxidation and membrane technologies and how well they perform. New technologies can come to site, can plug and play, and we can compare them to today's gold standards. Environmental impacts, we can measure all sorts of chemicals, but we really want to understand what the effects of multiple and complex mixtures is. So we can do that with the research streams and the dosing capacity. So the fate, the transformation, and the development of diagnostic markers and tools so that we have a good sense of what the best things to measure are to quantify those environmental impacts. Public health, we have 2 projects going on COVID surveillance right now. One was presented in a U Today article a couple of weeks ago. You can take a look at that. And I'm particularly interested in this one, using the chemical signatures of wastewater to understand what's happening in society. We're not trying to get into anybody's arm or their bedroom or their house, but we can look at changes in disease profiles based on the medications to treat those. We can scan about 110 pharma products, and we're just wrapping up a cannabis metabolite method so that we can start to look at medicinal and recreational cannabis use. And then these 2 themes that I'm going to touch on in a moment, antimicrobial resistance and microplastics. You're going to read more and more about both of these as time goes by. So just looking back, I'll touch on these really quickly. These are some projects that I've been involved with. So it's just a quick summary. Won't go in a ton of detail, but we have just on Monday in U Today at the university sort of revealed a data collaboration platform developed over the last 4 years with IBM called SWIM, Sustainable Watershed Integrated Management. Our governments say they're going to manage water resources at a watershed scale, but often that doesn't happen due to data siloing. And so we've developed a platform that gets away from the data siloing by providing a sandbox where everybody can contribute data, can go and get data, use it, and hopefully create some new learnings. I'm also very interested in retrospective analyses of the non-targeted analysis data that we have archived over the last 2 years. So as the next fentanyl or carfentanil comes along, once we know what it looks like in a chromatogram or where it's placed, we can go back and ask, did it just show up or has it always been there? We're doing a lot of work with hyperspectral sensoring, trying to understand the development of blue-green algal blooms. And in particular, some of my graduate students are working on microcystin production by blue-greens, so the toxins that blue-greens produce, which is really the blue-greens by themselves aren't the issue, it's the toxins. We've done some work with Trojan, and now we're starting to explore using machine learning and artificial intelligence. Can we take drone imagery through a project with SAIT and mine that drone imagery for data? So a whole variety of different things. And then, of course, we want to be pushing the limits all the time. So there was a project taking genes from bacteria, inserting them in algae. This is not going to replace traditional wastewater treatment, but it could have some sort of boutique use. So sewage lagoons, feedlot industrial waste, if we are putting in genes that are coding for enzymes that could degrade antibiotics or growth promoters, for example. Aerobic granulation, which has the capacity to really revolutionize the upgrading of primary to secondary treatment. You may have heard about this Village Blonde exercise from the fall where we took raw sewage, treated it to potable water standards, and then brewed beer with it with Village Brewery. And so the real win here, besides the social media exposure, was in creating the regulations around the water safety plan with Alberta Health Services. So this was definitely the first in Alberta, and as far as I'm aware, the first in Canada where these regulations were put in place for direct potable reuse. There were some regulations in place for non-direct potable reuse. And again, some rapid diagnostic tools. In the case of FredSense, it's for nutrient metals, and right now they're working on a SARS-CoV-2 rapid assessment. So what about plastics? We're hearing about this all the time, and this is a picture of a beach in Mumbai, and not all of this is plastic. This is broadly garbage, but a lot of this certainly is plastic. So there's plastic here, plastic here, plastic here. I mean, plastic here. You can look through this at your leisure and you will find an abundance of plastics. And we're hearing about plastics on this sort of scale quite a bit. In 2018, National Geographic published a special edition called Plastics or Planet. And here are a couple of interesting stats. 18 billion pounds of plastic ends up in the ocean each year. I don't know what that looks like in terms of volume, but it certainly sounds like a lot to me. And here's an interesting comment. Plastics aren't inherently bad. It's what we do or don't do with them that counts. And I agree with this to some degree. I disagree in the sense that I think plastics are inherently bad when we are being exposed to the plasticizers, the broad group of phthalates that have been shown to be endocrine disruptors and cause a whole host of problems. So yes, it's true that it's what we do with them that's important, certainly in terms of the garbage we produce, but there are some nasty, nasty things that are starting to emerge that I think we do need to be cognizant of. So this is really, a One Health issue. One Health is these large vexing issues in society that occur at the intersection of people, animals, and the environment. And this is a great example of that. People are responsible for the improper disposal of, in this case, it's fishing nets, which have a plastic component. They end up in the environment. And here's an animal that's been wound up in this sort of sensationalized picture of a turtle caught up in fishing nets. So these are One Health issues, and we have a new research program on the University of Calgary campus surrounding One Health, and I'll talk about that right at the end. Microplastics are a subset of plastics, and we're now even talking about nanoplastics, so even smaller plastics than microplastics. Microplastics are defined as plastic in the 250 to 5 micron to 5 millimeter size range. So this is 1/4 of a millimeter to 5 millimeters. And this isn't to scale because I didn't scale this picture. And they really fall into these 5 main categories. Pieces that have broken from larger plastic pieces, so fragments, fibers. So if you have a fleece, if you're an avid hiker, as I'm guessing many of you are, and you have fleeces, they produce fibers when you put them through the clothes washer. Foam, pieces of styrofoam, you'll see some of those in a moment. Nurdles, which are the plastic pellets used in manufacturing, and then microbeads. Now, microbeads were banned January 1st, 2018 in Canada, and all products, personal care products, could not use microbeads or contain microbeads effective July 1st, 2018. So you will only find these if you have personal care products. Maybe it's hopefully your toothpaste isn't 2 years old or 3 years old, but you might have, I don't know, some old sunscreen. Hopefully that's not 3 years old, or other things. But if there's some older things in your medicine cabinet, they may contain microbeads. And so primary microplastics are plastics that enter the environment as the microplastic itself, like a microbead, or it could be a nurdle. Secondary microplastics are plastics that are produced through the decomposition or breaking of larger plastics. So what does the science say about microplastic pollution, and why should we be concerned about it? The main concerns, at least to date, are over direct ingestion. Microplastics are perceived as food by a whole variety of aquatic or semi-aquatic organisms, and of course the microplastics have no nutritional value to the animals that are eating them. And it turns out there could be even some worse effects through the chemicals contained within the microplastics, and as it's turning out, the biofilms that are growing on the microplastics. The plastics, if they're broken pieces, may abrade the digestive tract directly. Lots of toxins are absorbed to the surface. We all have electronics in our daily lives, and so many of the plastics contained within those electronics are coated with brominated flame retardants to prevent them from lighting on fire. As the plastics are used and break apart, then we're exposed not only to the plastics, but the flame retardants contained on the plastics. That's one example. And the real big one is the release of chemicals that are used in the plastic production process. And so you may remember the bisphenol A, BPA fiasco that happened in 2007 when MEC, Mountain Equipment Co-op, pulled all their polycarbonate bottles from the shelves across the country. Manufacturers switched to bisphenol S or BPS, which it turns out is just as biologically active, but it wasn't regulated, while bisphenol A did become regulated. And so the concern is with phthalates, the same thing is going to happen. As some of the phthalates that are regulated become banned, manufacturers will just switch to alternatives that aren't banned, and then it'll take 10 years for the regulatory space to catch up. So there's been an outright call for a complete ban on phthalates. This group of plasticizers in the US, we'll see where that goes. Why are they a concern? And what do? They make plastic flexible, but they're not directly bound to the plastic itself. They're part of the resin mixture, but they're not integrally bound, and so they can be released as the plastics are washed, as they're heated, or as they break apart. So they're in medical devices, furniture, personal care products, cosmetics, in the bottles. They're endocrine disruptors. They affect the ovaries, uterus, testes, kidneys, nervous system, and thyroid. So we know they're biologically active. We know that people are exposed to them when they consume plastics or use plastics in their lives. For example, if you heat your food in plastic in the microwave, you're getting a dose of phthalates. And so, what we don't have is the framework in place to decide what safe concentrations are, if anything, and whether there should be an outright ban on them. And so municipal wastewater treatment plants are a large point source for microplastics because those plants accept waste from our home, from hospitals, industries, and we know that microplastics are generally too small to be effectively removed by most wastewater treatment plants. We do have the membranes in place to do that, but they're generally not employed by most wastewater treatment plants. So I'll just remind you of the wastewater treatment process quickly and then show you a project that's underway on microplastics at the Pine Creek Wastewater Treatment Center and ACWA. Raw sewage leaves our homes. It goes through coarse screening where everything that's larger than the size of the hole in this screen, typically around 5 millimeters, everything else is removed that's larger, and then this gets collected and sent to landfill. And you can look through this at your leisure, but there's a lot of stuff in here that is caught on the screen, and jewelry and dinky toys and condoms and tampon applicators and what looks like orange peel and all host of things, flushable wipes that people send down their toilets and drains, ends up at the wastewater treatment plant, and the plant has to deal with that right up front. So I'm going to be talking about raw influent, and it's this raw influent but minus the material that's been caught on the coarse screen. Primary treatment is physical. It's the collection of things that settle to the bottom and things that float, greases and oils on the top. The liquid that remains in the middle goes on to secondary treatment. In the case of the Pine Creek wastewater treatment plant, there's a variety of phases of bacteria, anoxic, anaerobic, and oxic phases, where the bacteria take up nitrogen, phosphorus, and carbon, incorporate it into their bodies, and then in the secondary clarifiers sink to the bottom and are removed as biosolids. So that'll be the second thing we'll be looking at, is the biosolids. The water that remains post-clarification goes to UV disinfection in the case of the Pine Creek wastewater treatment plant to inactivate any pathogens that might remain, and then that is released as final effluent, and that's the third thing that we'll be looking at. And of course, you saw the connection between secondary clarification and ACWA's research plants, where we have advanced treatment, including membranes, and then water discharge to the research streams. So here's the student, Paige is her name, and she's collecting final effluent and sampling water that came out of that ultrafiltration module. She's also sampled water on the influent side. And here in the background, you can see the reverse osmosis module. Again, there's growing concern over nanoplastics, and they should be caught by the membrane systems here. And so we're able to look at these membrane systems and what they're doing. So due to COVID, Paige's project, it's an undergraduate project, had to be reduced in scope, but she's got 8 weeks of samples at each of those 3 sites taken once per week. They were all collected and frozen. She determined the protocol to digest the organic material and did that by working on practice sludge from the ultrafiltration membrane. The digestion happens with 50% hydrogen peroxide, then the material is filtered, examined by microscopy, and also FTIR with a particular module. This is a spectroscopy process to try to examine the polymer in the plastic, and this can allow identification of the source of the plastic. So microplastics have been found in drinking water that's in water bottles, and the question is, well, is it coming from the water bottles themselves, or is it coming from the process that takes water from a source, goes through pipes, and puts it in the bottles? And so FTIR is useful in situations like that where you're trying to identify a resin or a polymer and attribute source to that. And then, of course, a variety of statistical analyses. So here's Paige. She's washing digested samples through that initial screen of 250 microns. So we haven't collected what's passed through that, but we will starting this summer. And then she collects that material, which then goes for further analyses. So here's final effluent from the plant digesting. You can see it's quite clear. Looks like there's nothing in it. Here's the peroxide, and here are control digestions. Of course, we're using plastic here with the peroxide, and the samples have been stored in plastic, so we need to know whether those plastics are contributing any plastic to the analysis. So of course, control. And here are biosolids digesting. They look quite a bit different. So here's a variety of organic material that's in solution during the digestion process. Here are the biosolids digesting away, and the bubbles are carbon dioxide bubbles that are released with the oxidation of the organic material contained within the biosolids. So we're reversing that process of photosynthesis that takes oxygen and water and creates carbohydrate, and oxygen as a byproduct. Sorry, it takes CO2 and water as the sources. So this is the reverse process. The gas leaves, and then what's left over at the end is this digested sample, and that's examined under the microscope. So here's some practice material showing the diversity of material that's caught on that ultrafiltration membrane. Here you can see some fiber, or some film rather. It looks like one of my contact lenses that I've dropped on the counter in the bathroom. You can't find. Here are some foam particles. Here it looks like either nurdles or microbeads. I'm not sure how Paige categorized those, but you can see they're very, very regularly shaped, and they have a crimp around the outside. These are probably nurdles. Here's a piece of foam. If you look carefully, you'll see fibers. And then the rest of this matrix is the bacterial community that's growing on the outside of the membranes and then has been back flushed off. So quite a very diverse and rich matrix of materials. Post-digestion, you can see there are materials that float and that have stuck to the side as that expanding, digesting mass rises up with the gas bubbles and then sinks back down. There are some components that are neutrally buoyant, and then there's a variety of materials down here in the bottom that are denser than water and sink to the bottom. So Teflon in particular, if you have Teflon in frying pans, for example, Teflon is about 2.2 grams per mil. Water's 1 gram per mil. And then some of these plastics, like the plastic that's in most of the drinking water bottles, the crunchy ones, that has a density less than 1, and so would float on the surface. And then after filtration, this is what is appearing on the filter. So again, blue plastic particles. These turns out are plastic foam pieces. We have some beads here of various shapes and sizes. Here's a yellow one. You can see blue ones, and then lots of smaller ones that on this filter are a little bit harder to pick out until you really work your way through the filter. So lots of material there. This is the raw influent treated and identified against a dark background. And you can see overwhelmingly, by number at least, fibers are the dominant microplastic that's contained in here. But you see lots of other things. There's a bead here, a bead or a fragment here, either bead or fragment. We'd have to look under a little bit higher magnification to resolve that. But lots of fibers in that influent. Here's Paige working away under the microscope. We built a holder for the filter and then a template so that she could go through the filter and keep track of where she was. And here you can see she's keeping track of the various fiber, nurdle, film, fragment, foam down here at the bottom. So even though that final effluent was really clear, it turns out that there is lots of material in there when you digest it and filter it and look at the filter. So this is the 47 millimeter filter. And here is a different filter from biosolids that's been cleaned up and zoomed in. And you can see a lot of plastic fibers in here. We don't know whether these were collected together during the filtration process or came into the wastewater treatment plant together like this and have made it the whole way through. But it gives you a sense of the diversity of particles that we find. And so the goal is to look at the influent, the biosolids, and the final effluent, identify whether there's any partitioning between these two final sources. These are the two sources that end up in the environment, which is what Paige is primarily interested in. But we can look at whether there is partitioning of different types. We can look at whether there's a loss of anything. We might be missing something between the influent and the biosolids. And so the questions center around the proportion of microplastics and whether they change during treatment. Is there any partitioning that happens between biosolids and final effluent? The short answer is yes. And does the amount of microplastics balance with what we're measuring in the biosolids and the final effluent? So are we missing anything somewhere in the process? And I'll just whet your appetite a little bit. The answer appears to be yes on that as well, particularly with those microfibers. Okay, so microplastics, you're going to continue to hear more about it. You're also going to hear about nanoplastics. So water reuse is something that's also on everybody's mind. I think most of you, if not all of you, know the South Saskatchewan River Basin is closed to new water licenses. This has been for over a decade now. Our cities continue to grow. Each of us uses on average about 300 or 320 liters of water per person per day. And so with continued growth, but effectively a closed basin, we're going to need to do more with the existing water or with the same if we can reuse it multiple times, which is one of the options to get more work out of the same. And if you're a new industry and you need water, you're going to have to purchase your water from an existing license. So there's a whole water market that is developing around that. Water reuse is where water is used, it's treated, it's used again, either for the same purpose or for another purpose. And this is part of the solution as water supplies decline and our populations and economies continue to grow. Probably the best example of using it again occurs on the International Space Station. Water is used, it's treated, and it's used again, and it's treated, and it's used again. And Robert Thirsk's expression is, my coffee today is your coffee tomorrow. And it's probably the longest standing example of water reuse, and that's direct potable reuse in that case. So once treated water is fit for a purpose and requires a water safety plan that acknowledges, depending on what the water is going to be used for, some level of treatment is required. Of course, the highest level of treatment is for direct potable reuse, where we're going to drink the water. But things like car and bus washes don't require treatment to direct potable standards to be used to wash our vehicles. So here's an example of direct potable reuse. Again, as I mentioned, to create that regulatory framework, ACWA partnered with Xylem, which is a technology provider, Village, and Alberta Health Services to create the first example of direct potable reuse, certainly in Alberta and likely Canada. So we took raw sewage, we treated it, and to potable water standards and made beer with it. So we worked closely with AHS to develop the water safety plan. I'll show you the essence of it in a moment. And during the production of the water to make the beer, the treatment processes were constantly monitored, and we used a third-party lab to confirm that we met all Canadian drinking water guidelines. And so the beer was launched on August 22nd, which is Earth Overshoot Day last year. And Earth Overshoot Day is the day when, in the year when we've consumed the interest on the natural resources that we're using on the planet. And beyond that day, we start to eat our way into the natural capital. And so like tax day, the day when you've paid your taxes and then the money is for you afterwards, this day is sort of marching earlier and earlier in the year as we eat into the Earth's natural capital. So here's the essence of the water safety plan. We had to meet in terms of log 10 reduction of, that's what these are, these log reduction values of viruses, and then 2 model organisms for bacteria, Cryptosporidium and Giardia. We had to meet 12, 10, and 10 was the regulations put in place. This is what we achieved with the various technologies, almost 15, 11, and 12. And then what wasn't included in our calculations and requirements was further treatment at Village Brewery with a reverse osmosis system and their processing. So they boil the wort to make the beer, and that creates a bit more reduction in viruses. So 1 log unit reduction is a factor of 10, 2 log units would be 100, 3 log units would be 1,000. And at the end of the day, we achieved, sort of 20 to 24 log unit reduction. So that's 1 times 10 to the 20 to 1 times 10 to the 24th log units of reduction of these required elements in the treatment. And as I said, we know these technologies exist because they're used elsewhere in the world, but the real win was developing that water safety plan, which creates the framework to now allow innovation in the reuse space, because there's the template in place to decide what the numbers are based on what the intended final use is. This garnered a lot of media attention. Probably some of you were aware of it. Even the mayor sent out a tweet. That always buys a lot of good PR for anything. I wrote an op-ed for Water Canada. Don't know how many of you read that, but it's got a readership of about 75,000, just talking about the process. I did some help with Diane Peters, who wrote this really interesting article in Future Human talking about how we need to start thinking about doing more with the same or less. And she focused on direct potable reuse, but of course there are many other uses that could be used with water reuse. And then I also wrote an opinion piece for Conversation Canada, just identifying some of the barriers and obstacles to implementation. The regulatory framework was clearly an obstacle, creating market pull to the technology developers, but also the ick factor is a clear barrier for some people. It's not a barrier for every people, but it clearly is for some. Okay, and that's a segue into antimicrobial resistance. One of the key limiters of what you can do with water, particularly for consumption, is that we need to make sure the water is safe. And so from a risk perspective, it's exposure to pathogens that are the real limiting factor today. Chemicals are to some degree, but I think in most people's minds, it's really the exposure to something that can make us sick that's really the concern. Superbugs are microbes that develop or acquire resistance to antimicrobial agents, whether that's metals, whether that's antibiotics, whether that's ultraviolet radiation. Most people are familiar with superbugs, but we tend to associate them, or the public certainly associate them, with hospitals such as MRSA, which is this methicillin-resistant Staphylococcus aureus. This is one of the nasty superbugs that people often acquire in hospitals if they do acquire something. But evidence is emerging that bacteria and wastewater treatment plants have acquired resistance to a growing array of antimicrobials, not just metals and UV radiation, but a very, very broad mix of antibiotics. And I think we're on the front edge of what we call an AMR tsunami that's about to hit us. This is what the public see in the media. Here's an article from Conversation Australia: rising antibiotic resistance in urinary tract infections could cost Australia $1.6 billion by 2030. And this is another National Geographic headline: first global look finds most rivers awash with antibiotics. And that's because we use medication to cure disease and fight illness, and we certainly should be doing that. It's a benefit of modern medicine. Wastewater treatment plants were never really designed to remove those, and because we release either the parent compound or a metabolite that is soluble and leaves in our urine, we're finding that the environment is the repository ultimately for many, many of these compounds. So here is some data from Calgary's wastewater treatment plants from a collaborator of mine, Tao Dong, in veterinary medicine, where Tao has looked at isolates from screening that the city is required to do as part of their reporting requirements. Tao then takes those isolates and he exposes them to antibiotics to see if they have any resistance. So here is the percent of resistant isolates, and here's the number of antibiotics classes that they demonstrate resistance to. And so if you do the math on this by adding up the height of the bars, over 50% of isolates that are resistant to antibiotics are resistant to 6 or more antibiotic classes. These are superbugs. And individual isolates are resistant to, in some cases, it's either 13 or 16 individual antibiotics. So that's happening today. And Some of those could be disinfected during the disinfection process, and we're very interested in understanding whether any of them are passing to the environment and surviving there. So this is kind of scary stuff. Why the focus on urinary tract infections? It's a model for what we think is going on with many things. There's 150 million UTIs globally a year. 40% of females will have one UTI in their lifetime. 11% over 18 will have one UTI per year, and many of these individuals will have multiple UTIs per year. UPEC, which is urinary pathogenic E. coli, a kind of E. coli found in wastewater treatment plants, account for 80 to 90% of community-acquired UTIs. And in the US alone, 11 million annual cases and $5 billion in healthcare costs were spent a couple of years ago. And so resistance is developing to a whole host of antibiotics that traditionally have been used to treat urinary tract infections. And when you think about it, in a return activated sludge systems, which many are, the bacteria that are part of that secondary treatment process where nitrogen, phosphorus, and carbon is being removed are mixing with pathogens. And we're starting to learn that there's a lot of exchange of genetic information, including the genetic code, the mobile genetic elements that are coding for resistance to this growing array of antibiotics. And so if the sludge is returned back up into the top of the process, the wastewater treatment plant has its own microbiome that is acquiring a microbiome resistance to a growing array of compounds. So we're looking at ozone dose and contact times to try to understand, are the current prescribed doses and contact times that utilities are required to follow, is it protecting us the way we assume it's protecting us? Can some bacteria survive those regimes? And if that's the case, what sort of antimicrobial elements are present? And we're also extending our analyses to agricultural operations, dairy and beef operations in particular, because we know animals are given antibiotics to treat their infections and illnesses. They release them into manure, and there's even less treatment in agricultural operations than there is in municipal wastewater treatment plants. So we have no reason to believe things are any different in agricultural operations. And so we also want to understand, if we do find genes in the environment, are they just there, or are they actually being passed around between bacteria, and are they conferring resistance to antibiotics? So we're going to do a bunch of experimentation to assess that by manipulating dose and contact times, and then surveying initially the wastewater treatment plants and agricultural operations, and then doing some experiments to see whether there is resistance to those elements. And so we have a new focus under the One Health paradigm that looks at antimicrobial resistance, healthy aquatic ecosystems. Clearly, wastewater treatment plants are front and center in these, and a couple other ones, infectious diseases in the microbiome, and healthy communities, which it turns out are related to these, because as we discharge chemicals and bacteria and viruses from wastewater treatment plants, if they do make their way downstream and survive and are somebody else's drinking water source, then we have a connection to those communities. And so, as I said, One Health is an approach that explicitly recognizes that infectious diseases result from this interaction between people, environment, and animals. And so I'll end with that and take some questions. I know that's a lot of material in a short period of time, but I'm certainly happy to answer questions that you might have. And here's some contact information in case the light bulb turns on at a later date and you want to ask a question then, or have a follow-up, or you want a tour of ACWA. You certainly can contact me, and I can put you in touch with my program coordinator, who can arrange for that as well.
Thank you, Dr. Jackson. That was really interesting. I'm sure there's questions. If you have questions, please type them in the question box, and we'll do a little Q&A. How did the beer taste?
The beer was really good. I would say that the water used, because of the amount of treatment, would have had less stuff in it, chemicals, large pharmaceuticals that are trapped by the reverse osmosis membranes, and certainly any biologicals than would be in traditional beer, because it was a very, very large amount of treatment. I've been brewing my own beer for probably 30 years. I couldn't tell the difference, and I would think most brewmasters probably couldn't tell the difference either, and they have very educated tongues.
Is it
Yeah, I was
still
fine.
available? Is it still available, and did it sell well?
So no, it's not still available. Yes, it sold really well. The can, I think it was either 3,000 or 4,000 cans, and it was gone in about 10 days.
Oh, wow.
It went like hotcakes. In fact, people have continued to ask, if they're going to do it again. It was a sort of a one-off pilot thing. I think it's not really where Village wants to sort of plant their flag in the sand and make a claim on using recycled water. I think they're probably moving on more to things related to taste than the sustainability aspect. But certainly there are other instances where this has been done. The Public Utility Board in Singapore produces a beer called Rebrew, and they've been doing that for years, and it's been done in Germany. So as I said, the real win there was in the policy development with the water safety plan.
Was the cost to make the beer more than the average beer, or is it something as an opportunity for some other microbrewery to get into, as a, so like you say, plant their flag?
Yeah, so it would have costed more because you need to pay for the infrastructure, the modules to do the treatment. It takes energy to do the treatment. You have to pay for lab analyses to make sure the water is safe to use. That's okay. But it's a very interesting question you ask, because you can then take that cost and ask, well, what is that cost being compared to? And I would argue it's being compared to water that is almost free, right? Because the water that comes out of our tap, if you look at the mill rate that you pay, it's only a small fraction on your water bill of what the true cost to produce that water is. And so, yes, it would cost a bit more, but I would argue we don't pay the real cost of the water. We get it almost free, and so we're grossly undervaluing it. And as there's more and more competition for limited supplies, that cost is going to go up. And at some point, those costs are going to be very similar, or consumers are going to make the choice that they want to support or consume a product that has a large sustainability component to it, and they'll be willing to pay a little bit more to have that product. So it's a really good question.
Is there a role or an opportunity for members of ACWA or other engineering companies, consulting companies, people working in aquatic ecosystems to get involved with your research, or what opportunities are out there?
So the answer is always yes. There's a variety of different ways. So for consultants, I think even having a tour and understanding the capability provides an opportunity when they're, let's say, creating consulting on a new development, for example, that might have self-contained water treatment. There's definitely a role in having the latest information and being well educated on the technologies that are available. So I'm involved at the national consortium that is pushing very hard distributed treatment systems, and that's really code for small systems. So we're of the opinion that if you build a new health center in a large municipality, it may not make the most sense to drive a pipe 40 kilometers into a centralized wastewater treatment plant where hospital waste is mixed with industrial waste and household waste. Maybe the best option is to use specialized technology and treat that waste on site. Or if you build a new community 20 kilometers outside the city of Calgary that's not within city limits, maybe you put on-site drinking and wastewater treatment and have that self-contained. In that case, and so you don't drive the pipe, the 20 kilometers and the cost of that. I know there's some benefits to consulting companies in encouraging that, but I think we need to start thinking really differently about centralized versus distributed systems. And certainly for remote communities, there's a role for distributed systems. So there is definitely a role on that side, and helping their clients understand what options are available, what the pros and cons are, and helping their clients decide what the right decision for them is. Absolutely, there's a role.
Yep. And there's a huge cost involved with the farther the community is out, the farther you push water and waste back to a central facility, the cost of the energy and dollars to do that is extremely expensive when compared to you could make a centralized facility, like you said.
There is, and I didn't talk about the cost to build ACWA, but the most expensive part was the research streams. Part of it was the earthworks to pour all that clay and carve it. But we drove that pipe from the intake building up to the head pond. That was about, as I said, 1.4 kilometers with a 9-meter elevation change. And that was really, really expensive to dig a trench, to put a pipe in to go 1.4 kilometers. It was hugely expensive. The pipe was expensive, so I agree completely. And then with a water safety plan in place in a remote community, you can then use that water for something else. Or you can use the energy you capture from the waste for something else. So in a remote community, you can anaerobically digest the waste, you can create biogas, you could heat a greenhouse, you could light a greenhouse, you could power your water and wastewater treatment plant, and now you have safe discharge of the water. Or you can water gardens, or you can flood rinks, or you can water parks, or you can do all sorts of things, provided the water safety plan is in place.
Great. Yeah, I see opportunities next time we're allowed to have in-person events. So I'll definitely have our group, whether it's our conference next year in Calgary. We always do a site tour or something. Maybe we'll do the ACWA facility and include that as part of our program. Were there any additional tests done on the treated water use for the beer beyond what was required in the Canadian drinking water guidelines?
So what sort of additional tests? I mean, those are the most stringent requirements, and those include metals, organics, and pathogens. So, and the full suite was done.
They added like pharmaceuticals.
So some pharmaceuticals are included in that as well under the organic suite. So yes, those were done. We also did analyses in our own lab, but those weren't part of the reporting because we wanted an independent evaluation of the water. We didn't want to be sort of certifying our own water. If that makes sense.
Does anyone else have any other questions? If so, we'll take another minute for questions if there's anything else that pops up. Once again, reminder that the webinar will be available online later today at esa.org/webinars. Reminder to check out esa.org/envirotech virtual edition for the call for abstracts. The event will be in June. And with that, I don't see any more questions. So Dr. Jackson, thank you again for doing this. Really appreciate this. Thank you.
So I have one question for you just before we sign off. Okay. We've thought about creating continuing education programs, and so if there are needs that your members have that you think we could help contribute to, whether it's improving statistical analyses and quantitative tools, anything on water treatment and the technologies, we'd like to hear about that, and we would be interested in partnering on that. But for us to assume we know what you need from an educational perspective is probably not the right way to go. We'd like to hear from you. And so if your members have any suggestions or requests, we'd be more than willing to listen to those.
I will get in touch with you and get back to you. We also offer courses and are always looking for content and looking for instructors and people to partner with. So that'd be a great fit. And I'm sure we get some feedback from either people attending can email me or I'll be in touch.
Sounds good.
Okay. Thank you again, everyone. Thanks for joining us today. Watch for our next webinar on April 15th. Until then, thank you and stay safe.
Thanks, everybody.